Swayam Prabha. Digital India. Educated India.
So for example, if we go back and look into our generic optimization problem, then here if we see that x1, x2, x3, if they appear in the objective function as a product with certain power raised, then that particular problem becomes geometric programming problem, and that type of function can be there in the objective function as well as in the constraint. Now similarly, apart from the geometric programming problem, a quadratic programming problem is the one where the objective function or the constraint have quadratic equations. If the constraint and the objective functions all represent linear equation, then we call it as a linear programming problem. It is important to identify the nature of the equation involved in the optimization problem, because it is going to lead to the solution method involved. Each of these different type of programming problem or optimization problem have different solution method or technique. We'll learn more about that from the next class onwards. Now if we look into the permissible values of the design variables, we'll find that an optimization problem can be considered as either integer programming problem or real valued programming problem. In an integer programming problem, the design variables or decision variables represent only integer values. Sometimes this integer value could be only 0 and 1. In those cases it becomes a binary, otherwise it becomes integer programming problem. For example, if we want to optimize the number of people required to construct a masonry wall, in that case the number of people required can be only integer. Any problem which represents that will become eventually an integer programming problem. On the other hand, if the variables represent the real value, then the problem is known as real valued programming problem. The deterministic nature of the variables also help to define an optimization problem. It can be defined as deterministic programming problem or stochastic programming problem. In a deterministic programming problem, the variables remains constant and we consider them as a fixed value. Whereas in the stochastic programming problem, the variables could be of probabilistic nature. For example, if we want to design a pavement and we are considering the variability of the resilient modulus of the material used, then the problem becomes stochastic programming problem. Another example could be if you are considering the allowable stress of a concrete while designing a column or a beam, then we know that the allowable stress for each sample we test is going to be different. If we don't choose the 85th percentile of that or 95th percentile of that value, we may choose rather the probabilistic characteristics of that value. And if we try to choose the probabilistic value, then it becomes a stochastic programming problem. The variables which are there in the optimization problem sometimes can be easily separated from each other, particularly when these variables are not dependent on each other in the problem. If we can separate those variables, it becomes a separable programming problem, and we can individually optimize this variable for a overall problem. If those are interrelated and cannot be separated, then the problem is known as non-separable programming problem. Another important classification of optimization problem is based on the number of objective functions. Now the equation which we showed here, if we have only one objective function, then it becomes a single objective function problem. If this is represented by multiple functions, then it becomes a multi-objective optimization problem. Based on the number of objective function, we are defining it as single objective or multi-objective programming problem. Now let's look into the steps to optimize a particular problem. Before we start the optimization, we need to understand what is the need of the optimization, what we are trying to optimize. Once we understand that, it will help us to identify the parameters involved in the optimization process or in the design. Once we find out those parameters, then we choose the boundary condition. So each variable might have certain boundary condition and we can easily select. Once we know the boundary condition, then we like to formulate all the constraints associated to the optimization problem, and then we also formulate the objective functions associated with that problem. So these are the few steps which we should go through before we can formulate and start solving an optimization problem. To solve, there are various methods. The one of the method which is well known is the classical method, and most of you are familiar with it. This classical method is generally or easily applicable to the unconstrained optimization function. It can have single or several variables. The primary criteria of applying classical method are: the function should be differentiable at least twice with respect to the design variable, and the derivatives are continuous. It becomes difficult to optimize a problem with constraints. We cannot use the classical method without any modification to the problem. So there are a few techniques depending on the type of constraint to convert a constraint optimization problem into an unconstrained optimization problem and then use classical method. For example, if constraints are of equality or equality constraints, we can use Lagrange multiplier method. On the other hand, if the constraints are of inequality nature, we need to use Kuhn-Tucker conditions. Now in both cases, the Lagrange multiplier method and Kuhn-Tucker condition, the converted unconstrained optimization problem could be complicated to solve, and in those situations the classical method of solution where we use the derivative may cease to exist or could be computationally inefficient. In those situations we use numerical methods to solve those problems. In this class we will go through certain numerical methods to solve such complicated optimization problem. The other optimization techniques which are used are nonlinear, linear, geometric, quadratic, or integer programming. The names represent the type of the problem or the class of the problems. If you recall, we had discussed these different types of optimization problem in one of our previous slides. As I said, anything apart from the classical method involves numerical method or numerical technique. So all these methods employ the numerical technique where we sought to get an approximate solution by following certain iterative steps. Generally this method starts from an initial solution and progress towards the approximate solution available in its vicinity. Apart from these methods, there are also methods involving genetic algorithm, simulated annealing, particle swarm optimization, ant colony optimization, neural network based optimization, and fuzzy optimization. We may not be able to cover all of this, but if time permits, we'll try to discuss about one or two of the evolutionary algorithms in optimization problem.
So in today's lecture, we came to know how a descriptive problem can be represented into a mathematical formulation of an optimization problem. In this optimization problem, we also saw the various components such as objective functions, constraints, decision and design variables. We got to know the difference between the decision and the design variables, and in the process we also looked into the classification of the optimization problem based on the existence of the constraint, nature of design variables, physical structure of the problem, nature of the equations involved, the permissible value of the design variables and its nature, the type of separability of the functions, and the number of objective functions involved in the optimization problem. With this insight, we'll move into our next class when we'll learn how to solve a single variable optimization problem. I hope by the end of this course, you will be comfortable enough and confident enough to solve optimization problems needed in your engineering processes. With that, thank you for today and see you in the next class.